Today, we are going to look at the winning solution from the KDD Cup 2024. So this KDD Cup is actually hosted by Amazon, and it is titled with Multitask Online Shopping Challenge for LLMs. So the goal is to build a LLM assistant to answer all types of questions regarding to online shopping. You can find all the workshop informations and also the winning solutions, all the winning solutions other than the first place winning solution I'm going to present today. You can find them all at this Amazon KDD Cup 24 GitHub link over here. And also you can easily just find it, find the Amazon KDD Cup 24 just by searching Google, and you will able to get all the material resources on this. So to begin with, I want to just look into what exactly the problem we are going to solve. So there are 5 tracks over here. So the first track is about understanding shopping concepts. So the shopping concepts can be, what product types, what are the product attributes, etc. About the product, right? So all the concepts regarding, what specific items you want to look for when you shop on Amazon. And then there's like a shopping knowledge reasoning to see, for example, whether this product is compatible with the other product. So this is like a reasoning part. And also the user behavior alignment to identify the most relevant items to the user query. I guess you all have searched on Amazon, right? So whenever you put in the search box, Amazon tries to try to identify the most relevant products to your search or query. So that's user behavior alignment. The fourth track is the multilingual abilities. So basically, Amazon is like a global e-commerce, right? So they list all the products in various languages. So basically, you need to understand all of this, like the first 3 tracks, shopping concepts, user intentions in multiple languages. So is this specific focus on like multilingual abilities to test all these different tasks in non-English, like in addition to English. The fifth track is basically a mixture of all 4 tracks. So basically you get the results of all 4 tracks, and then you get your overall ranking final placement for the fifth track. It's the all-around track to really have a solution for the multitask, like including all these tasks for the online shopping experience. So that's the overall problem statement. So here is some examples of each of the individual track. First, on the shopping concept. So this more related to the name entity recognition, right? For example, the query is this, and then the question to the LM is to extract phrases from this query that correspond to the entity type product line. So which of these word here corresponds to a product line? So the ground truth is X470, right? So it's kind of extracting the most relevant word from the queries. The second track, the shopping knowledge reasoning, is to test about the product compatibility. For example, it gives a multi-choice problem, like the 0 is one product, the option 1 is another product, and then it asks to identify which of these item is compatible with Apple Lightning this headphone adapter, right? And then the model is to select one of either 0 or 1. So it's kind of like a multi-choice. And then the third track, user behavior alignment. So this one is to figure out what is the user attention, right? So for example, this is a shopping session of a user. The user typing the query keyword is this, and then it click on certain products, right? It may click on multiple products over there. So this is called a shopping session for a user. And then the question is, based on this shopping session, like the user action over here, what is the correct, like most likely the correct intentions of the user? What is exactly the product that the user want to search? Again, it's like a multi-choice over here. And the fourth one is the multilingual. Basically, so this is, I guess, is in Spanish, right? And you need to understand the Spanish. You also need to answer the question in Spanish. Yeah, so this is multilingual. So this is all the tracks for this multi-task online shopping. An overview of the data set. So there are about 57 tasks uh, in five task types. The task type is like the format of the task, right? As the example we have shown earlier, is all multi-choice. Basically, you give a question and also you give several choices and ask the model to select like one correct choice. It can also be retrieval, so to identify all the relevant items satisfy the requirement. It can be a ranking. For example, given the user query, just rank the most relevant products according to the user query. So that is a ranking. Name entity recognition, you need to extract the piece of text from the input and then identify what is the corresponding text that falls into the entity type. The entity type can be, for example, what is the size of the shirt, right? So if the product description set is a S, is a L, so basically you need to identify extract the phrases from the text that corresponds to the target entity type you want to predict. And then the last one is the generation. Basically, that is what LLM is good at, is just, generate a response, generate a text following the instructions to the question given the context. So these are all the five task types. And it corresponds to 57 tasks. So basically, you can combine all the products, all the user intentions, search queries, etc., to formulate like a different task. So there are like a 57 tasks. There are about 20K questions. So basically, there are 20K or so queries to the LM. So this is a test data set. There are about 13K products, 400 product categories, 1K product attributes, and about 10K customer reviews about the products, and also about 4.5K user queries, kind of like the search queries to the products. So this is the competition. They mainly just released the test data set. So they just tell you, oh, okay, we have like a test tab, they call it like a shop bench. So this is going to be the final test data set that will generate the final test evaluation score and going to rank all the submissions on the leaderboard. And then you may question what is the training data set, right? And I will get to it later. So this is the summary of the competition. So basically, it's evaluating large language models as a helpful assistant in e-commerce domain for the online shopping. So the competition released a test data set they call Shop Bench that contain 20K questions. So basically, it's like 20K samples you need to evaluate. Like you need to generate a response and will be evaluated against the ground truth there, and it's covering quite diverse tasks and various diverse product categories and attributes. And actually, it's also a code competitions because you basically you have no access to the test data set. They just tell you there is a test data sets of 20K at backend for the evaluation, but you actually have no access to the test data sets. It's like hidden. And the solutions you need to submit the solutions there, and it's going to run on cloud and directly with the time constraints there. So basically, you need to upload your model, and then it's going to run like on the host provided by the provided by Amazon, right? And then there's a strict time runtime limit for each of the track. For example, track one, you need to finish up in 70 minutes, track two, 20 minutes. Like to finish all five tracks for the 20K questions, you need to finish in 140 minutes. And if you do the calculation, so basically per question, maybe not per task, it's like per question, you need to answer give a response. The LM is required to generate a response within zero point 0.5 second, like around 0.4 second. So that's the challenges. And so basically the challenge is like no training data. So actually they just provide 96 example questions from this short bench data sets just to give an idea about exactly what kind of task this evaluation data set is about. So they just share like 96 examples. And these are all hidden. So these 96 questions, because we know it's like there are 57 tasks, but they only cover 18 out of the 57 tasks. So the generalization capabilities of the model is extremely important, right? Because you don't even know what are the other tasks is in your test data set. They just give you examples of the 18 out of 57, and for the rest, you would bet that your LLM is able to generalize well to other tasks. And also, like as I mentioned about the runtime limit, right? So there is a time and compute constraints. So the solution is to run in a specific time on a four T4 GPUs, and each GPU has like a 16 gigabytes memories in there, which means that you need to do some LLM inference optimization to limit the memories and also optimize the inference speed so that your inference can finish up within the time limit for all the 20K questions in the test dataset. Okay, so that is all the problem. Like what is exactly the problem and what are the available data set? Actually, there's none data set, to be honest. And what are the challenges, right? The challenges is like no data, hidden task generation is a key, and also it's also a code competition that requires the memory and inference time limit. If no question, then let's move on to the winning solution. The winning solution is from NVIDIA. It's a team of 6 people around the globe. And so this is their, maybe let's see the final results. So the final results is basically a score between 0 and 100. And so they are able to win the first place of all the track uh, with one LM. They fine-tuned. And this is also the score for the second place and third place. And we see that for some track, for example, track 4, this is a multilingual track. They show like a significant improvement over the other submissions. Yeah. So this is a high-level framework of exactly how they build out the winning solution. As you remember, there's no training data, right? So they synthesize the training data. So basically, they collect lots of public data. I will show the list later, but they collect first lots of public data sets. Also, Amazon has released some open source data, like in 2023, like around 2023, on the shopping challenges, other shopping challenges, and also customer review data set. So basically, they take the seed from the open source data sets, and then they synthesize a lot more training data sets, considering the task types in this competition. So they use Llama GPT-4, also like a human as a seed input, to create a 500K plus examples of 40 tasks. So because we know the competition kind of tells you what type of task it is, right? So they basically just synthesize the training data according to all this task type. And then after they create the training data, they fine tune the QM model of course, like as the first step, you are going to evaluate the zero shot, like non-fine-tuned version of all the LLM. And then they identify the Q172 billion gets the best zero shot performance without any fine-tuning. So they choose this as their LLM backbone, and then they fine-tune it with QLoRa on 8 GPUs. So this is like a low rank representations on the adjustment of the weights in the LLM. And then in the end, they also doing some like quantization, inference optimization, so that these Q1 models can be loaded to the smaller GPUs like provided by Amazon in the end. So this is a high level framework. So as I can tell, the key differentiating part is the training dataset creation than the other solutions. So I think we will spend much time on the training datasets and how they exactly create the training datasets. So this is the input sources of all their training datasets. So including the Amazon M2 multilingual dataset. So this is originally released for KDD Cup 2023. And also it has like Amazon review datasets. It has like 500 million customer reviews across like 33 categories. So I think this dataset will be very important because it kind of tells the pre-knowledge of the Amazon products and also how the users is going to interact with on Amazon, right? So these are kind of like Amazon related, directly related public data sets. There's also like the e-commerce instruct dataset. It has about 100K samples from 10 e-commerce tasks, including attribute extraction. So this is more like name entity task, right? Like product relation prediction, product matching, sentiment, etc. So this is like a instruction dataset for e-commerce. And like this ESCI dataset, so E stand for exact, substitute, complement, irrelevant dataset. So this is to compare basically to compare the relevance of the product to the user search queries. So these are kind of like a general e-commerce related datasets to help understand the e-commerce products, user queries, interactions, and also the product interrelationships. They also use some public general NLP benchmark like language understanding pre-training datasets to basically improve or maintain the LM capabilities to answer the multi-choice questions, right? Because this MMLU dataset has lots of tasks consisting of like multi-choice questions. So in order for the LM to answer the multi-choice question, you'd better have a data set just to help the LM to understand like what is the format of the multi-choice and how to answer multi-choice questions accurately. They also use the Alpaca dataset. So Alpaca is also a synthetic dataset created by Stanford, like for the model distillation. It is synthesized by GPT 3.5 like kind of like an instruction flowing dataset. So they are keeping this dataset so that the LM can follow the instruction in that process. So this is their strategies to how to curate the synthetic dataset, right? So they can prompt the LM to construct the task directly, provided the dataset. For example, you can ask the LM to combine the product attributes, entity, and the instruction together into a task. And also you can combine the user query, product list, and instruction together into a different task, right? So you can actually ask the LM to construct the task itself. You can also enrich the C data with the missing details. For example, there's a product description, but it doesn't have, say, the size of the or the version of the laptop, right? So you can use the input and then prompt the LM to generate these additional product attributes related to that products. And also, for example, identify what is the product type or categories for that given product description. There's also like generate instructions with different wordings, because you can imagine all kinds of ways to write the instructions there, right? Still meaning the same thing, the same response, but you can write the instructions in many different ways. So this kind of gives more diverse inputs to the LM to understand the instruction and understand the relationship between the instructions and questions and the response in the training data set. So in the end, they create 38 diversified data sets. That gives you about 500K samples. And if you look at where this data set, what is the source of the data set, right? So some are seeded from the e-commerce instruct data set, some are seeded from the language understanding data set, and there are also a percentage like this from Amazon, like Amazon open source reviews and Amazon M2 multilingual data sets. And this is also the distribution by task type. So actually you can see like majority of the task type is from the multi-choice. And then the next is the generation task. Okay, so that's the data set. And this is like some examples of how they create their training examples, right? For example, this is a product title, right? And then it asks like which of the following reviews was written for this product. What it can do, it can just directly grab ground truth. Like we know there is a customer review for this product, right? And it just insert it in as an option, and then you can generate some other random irrelevant reviews. And of course, you know the ground truth is two, right? Because you grab this data set from the Amazon review data set. So you know this one is the correct answer, but you can generate all the other random irrelevant reviews along and prompt the LLM to select the right answer in the end. So basically, this is like how they create like synthetic data set. And also over here is like ask it to rank the reviews according to their help list to a user. For example, the product. So again, given the product title of this, and then there's like a 5 reviews, and then you are going to just rank the reviews to see how helpful that review is to a potential buyer of this product. And also this is like a query based, right? Like rank the queries according to their relevance to a product. Given a product title, how relevant this queries according to the product title. And again, the expected output is going to be a ranked list of the queries in the end. So that is their data set. So this is like 38 data sets. And you can see this is a source data set. The task is the specific task in the competition. So basically they correspond according to that task, they create that synthetic data sets with the examples or seed data from this source data set. And this is the task type is a multi-choice. Like for example, this task 2 is about select the product categories given the product attributes, right? So I can tell you the color, the size, and I think the size tells a lot. And then you can guess, okay, what are the potential product categories given this? Um, and yeah, so basically they generate, so this is all their source data sets, as I explained. And then this is the list of tasks in the competition, also the type of the task. And then this is how many synthetic data sets they're able to create from this for this task. So this is like they build like 21 data sets. Is close to the KDD Cup. Basically this Amazon KDD Cup existing task that they know, right? Because like they haven't fully disclosed all the tasks. They just give you a few examples of some of the tasks. So basically their idea is like, oh, maybe we can add more tasks because we don't know the full scope, right? So they get some new ideas about okay, how can we create like additional task beyond what they know from the examples, from the few examples. For example, like explain the product type, given the title description, and also select the user query that match the product description. I think these tasks will all make sense in terms of, under the online shopping background. I think these tasks are all valid tasks, like or pick three bullet points to match the product, etc. So basically, they even diversify the dataset by building another 17 datasets, so about 150K samples by implementing like exploring additional tasks beyond the few examples that provided by the competition host. Yeah, so the phase one is they want just to evaluate the zero shot LLM out of the box, without fine tuning at all. So they just focus on the prompt engineering and model selection. So this is Bagel. Actually, I don't know these models. I think they are variants. For example, this one may be a variant of QM model, and this one is another variant of uses the same architectures as Llama, but they train their own way, kind of. And then this is like Llama 3. I think you all know about Llama 3 and also the QM model. And then basically like they focus on what is the best prompt. For example, they can begin with you are a helpful online shopping assistant, right? To set the tone for the LM, and then they just like provide examples, and then they just indicate the task type and instructions and directly report what is the performance for all these five tracks. Um, and in the end, they find that like this Q1 72 billion model uh already received like a good performance. I mean, although not the best performance, but already shows that it can generalize to all these tasks pretty well, even though without any fine tuning. It specifically mentioned that the 70 billion model without fine tuning would score like ninth place overall for on the competition, and the fourth place especially on the track five at the end of the competition. So basically, according to the zero shot performance, they pick the Q12 model as the base model for the further fine tuning. Fine tuning Q1 2. So they fine tuned with the QLoRa, so it's quantized low rank adaptation. And using this library. So I think if you are interested, you can search this axolot L library. I look at it, it seems a pretty like easy to use library that can support the fine tuning. Support the fine tuning of various the LM models, including Llama models, QM models, mixture models, etc., etc. Like a one library, one framework to fine tune various types model, and also offering like a different support for multiple configurations. For example, you want to fine tune with QLoRa, so it's kind of like a one config in the fine tuning of exactly what technique you want to fine tune. And the fine tuning can run. So basically they use this to fine tune the Q1 to 17 billion on the 8 GPUs, 8 A100 GPUs for 24 hours on those 500K synthetic datasets. And the loss is calculated, so it's just a supervised fine tuning loss. It's just a direct token loss. They haven't applied any reinforcement learning like for the human preference, because the answers is quite straightforward, right? It's like a multi-choice. You know exactly the answer there. Like you don't need user preference optimization for majority of the task over here. So they assume that the reinforcement learning with human feedback is not required because the answers are quite straightforward and it's fixed and also contain very few tokens in the end. And also they say like system prompt contains a task type. For example, you are helpful online shopping assistant, the task type is this. And then they provide the task type, and then they use some simple heuristics to determine what is exactly the task type over there. So using the QLoRa fine-tuning on the 500K, they're able to show big improvements in terms of the performance, especially as you can tell is the track 2 and the track 4. Track 4 is the multilingual one. Track 2, I think, is about the shopping knowledge reasoning. For example, like whether this product is compatible with that one, right? I think the fine tuning will be very helpful, especially if such compatibility information is missed in the pre-training dataset. And by showing more examples to learn about this, how to tell this product can be used along with the other product in the fine tuning is going to greatly help with the performance over here. And this is all their hyperparameters configurations. I think most important ones is one is the quantization. So they use 4-bit quantization in their LoRa fine tuning. It's like a 4-bit quantization. And also the hidden dimension, the rank of the QLoRa is 64. So these are kind of the key parameters there. After fine-tuning, they also applied weight space interpolations for fine-tuning called a WISE FT. So this is mainly to deal with the distribution shift between the pre-training data and the fine-tuning data set. This interpolation weight is mainly to prevent overfitting. Because so basically just a linear weight interpolation. So this is your original LM weight, like the pre-trained say QN2 model weights, right? This weights is kind of strong on any distribution. So basically in your pre-training data set, like the full scope of the world knowledge, you can think about that way. So it's kind of like a strong on any data distribution. It's not specifically for any domain, specific domain. So it's like a zero shot on the full world knowledge, the base knowledge. And then after fine tuning, you get a new weights, right? And this new weights is specifically for that specific domain. Like for example, it's specifically designed for the Amazon shopping domain, right? So it will be strong on your domain data set. And people may find that if you just use the fine-tuned weight over here, you may see a dramatic loss of performance on the other task. Maybe you can answer the Amazon shopping question very well, but you may lose some capabilities to do the general reasonings and general language generations there. So people propose a way to do a linear interpolations, right? So just like a linear weights to combine the original base model and the fine-tuned model weights together. So this is the WISE weight. And of course, like QLoRa for formula is like you just do matrix like lower rank matrix multiplication and then multiply this together to adjust the base weight. And then if you put this in the end, you will get the base weight plus alpha, and this is your LoRa low rank matrices in the LoRa adaptions. So basically, they need to just rescale the LoRa weight weight A and weight B by a square root of alpha. And actually, this method has also been implemented in the PAFT. It's kind of the very popular package for the performance efficient fine tuning methods. So there's also there's a rescale adapter scale over here. And another idea they talk about is ensemble the adapters. So if you think about the adapters over here, you can think about the weight matrix, the weight matrix of A. So these are the adapters basically. So this matrix is kind of like adjust the base weights so that you kind of adapt to your training data set, your domain data set. So this WA and W here is kind of the adapters as mentioned over here. So basically, I don't know exactly how they speed up the data set, but it seems like they out of all these 38 data sets, they separate these data sets to different groups. And then they are going just to fine tune the model based on that subgroup data sets. For example, over here, like there's a V8 data sets, almost covering all the data sets except for some of the ESCI data sets, like this V8 and also V7. And then they also developed some V7B and V9B like group of data sets. I guess they may have like tried multiple combinations of data to see, okay, which combination of these data sets are can approximate the final test data set well, right? So I guess they have explored like a different combinations of this data set in their for their fine-tuning process. And then by combining different data sets out of the 38 data sets they created, they have like they train like different adapters for that. For example, for track one, they mainly use the adapters from V8. So V8 is a group of data set out of those 38, right? So it's like they find that using the V8 combination data sets, they can get the best performance over there. And also for track two, even though it's the same like a Q1 based model, but they use like the V7 datasets to do the Q-LoRa fine tuning, etc. So basically, like a track one and track three and track five, they are using the same dataset for the fine tuning, and track two and track four are using the same dataset over there. So this is their first iterations. And they actually do another iteration, a second iteration. The second iteration is depending on the exactly what data set you want to further fine tune the model. Right? Again, like track 1, 3, 5 are using the same data sets to do a further fine tuning, and track 2 and 4 are do another. So basically they are able to see some additional gain, but I would say it's maybe not needed. Like using their iteration one, they're already winning the competition. But good to see like they're also trying to do okay, whether there's any additional fine tuning needed to further improve the performance over there. And this is some of the exploration they share, like using different combinations. So each V7, V8 over here just tells you like a different fine-tuning data set, right? And alpha here, alpha is from the linear interpolation of the weights. And you can it shows that using different fine-tuning data sets and setting different alpha, you may observe like a different final performance there. For example, like if you use V8, and then the best alpha config will be around 0.55, I think, like over here. Yeah, so basically it's like the Wise linear interpretation helps control the overfitting, and then the dataset combination is trying to get to the final domain, the test domain of that shop bench uh, data set as close as possible. So basically, they're trying to mimic the final test domain as close as possible by exploring the combinations of these data sets. After fine tuning, they also like apply some constraints to the LLM outputs because the competition, right? So you need to upload the model. If your model fails to generate the desired format, that response is going to be considered as wrong response, right? For example, if it is a multi-choice, if you generate a 7, basically there's no option for 7 there. Say the LM hallucinate and you generate 7 there, then basically that response is considered wrong for that query question. So basically they want to process the outputs of the LM to limit the outputs of it. For example, for the multi-choice, it just limits the LM output tokens to be among the listed options in the instructions. Like they just limit the output to one of these tokens in the output. And also like for retrieval and ranking, they also force it to be like numbers separated by commas. So the LM is forced to generate this, so that it doesn't generate lots of wasted tokens there. And also for the name entity recognitions, because we know the name entity must exist in the prompt, like in the product description provided in the prompt. So basically they increase the largest of prompt tokens. Basically it's like the final output has a higher chance of picking the tokens that already exist in the prompt because it's name entity recognition, right? So the name entities must already exist in the prompt. And then for generation, then there's no constraints over there at all. So basically they do some post processing to the LM, so that it can like to generate the exact format of output from there. If you want to understand like what is the logits, so the logits are basically the outputs of the final layers of the LM of the neural network, any neural network, not limited to LM. So it's basically the outputs of the final layers before you apply the softmax or any activation functions. So these are the raw outputs of the final layers of the neural network. Okay. Uh, Lastly is about the quantization and inference acceleration. As you know, like because the host only provide like 4 by 16 gigabytes GPUs, so that is in total 64 gigabytes of memory. So it is too few for like a Q172B if you want to load it in float 16 like a 2 bytes, then it's going to be like a 144 gigabytes, right? Like multiplied by 2. Like without any quantization, you cannot even load the model into the GPUs. So basically what they do is they merge the LoRa adapters into the weights and then quantize them into 4-bit using the AWQ. So it's the activation aware weight quantization. You can also directly just quantize the weight into 4 bits. But this AWQ action aware weight quantization actually will improve the accuracy comparing to non-activation aware. So that it makes sure that the weight is scaled in the right way, and all the quantization range is utilized for the quantization. And they use the 96 QA peers, the examples for the calibration, so for the quantization calibration, and takes about 1 hour on a single GPU. And they claim that these 4 bits quantization gave similar results comparing to the original non-quantized version of the QM model. So that's on the quantization that solves like to load the LM into the limited memory. The second is about how to accelerate the inference by fully utilizing the distributed like a 4 GPUs over there. So they use VLM, it's kind of like a virtual LM, by basically like padding the multi layer perception layer like to the exponential of 2, right? So it's kind of like you need to make it, for example, the 768. If it's like a length of 768 rows of the matrix, you want to add it to the nearest the exponential of the 2, which is like 1024. So that and all the extra columns are filled with zeros. Uh, the paddings they ensures that during the GPU execution, the matrix are directly aligned in the GPU memories, like in the full core, and there won't be any memory fragmentations, and also it can speed up the operation across the GPUs. There's also a paper specifically focused on VLM. to in terms of the distributed inference of the LLM and how you can add it to the right dimension so that the LLM can be distributed inferred across different GPU machines. Okay. Yeah, so that's basically the full solution of the first place. And I feel like the key part, like comparing to other solutions, is their ability to create the 500K examples. And also, I think the fine-tuning part is standard. Yeah, like I think the QLoRa fine-tuning part is standard. The main key part is how they create a diversified examples. um, Given the few examples like provided by the competition host. Yeah, and then they're able to do the inference optimization so that they can finish up all the tasks within the time limit. And yeah, so this is like I think exactly this is their final performance over there. And I think there is like if you look at some other winning solutions, there is also a fully zero shot second place performance for not for all tracks, like for example, just for track one or for track three. But like to win them all, like win all five tracks, or I think the fine tuning is still a must to really, understand the Amazon domain dataset and understand the product compatibility relationship. I think the fine tuning will still help in this sense. But even without fine tuning, for some of the track, there is some just zero shot. Just focus on prompt engineering, you can still get to second place on some of the track over here.